Are these grid or ground coordinates? This is a sentence I've probably said 1,000 times in my career. I'm essentially asking if the set of point coordinates I've been handed are in a known grid mapping projection. Why do I care? I care because if I don't know and assume incorrectly, I could be unknowingly adding in a massive source of systematic error. I've seen this firsthand numerous times where a surveyor assumed coordinates were in grid when in reality they were in a ground-based coordinate system, and the consequences are oftentimes very significant. I've seen projects delayed months at the costs of hundreds of thousands of dollars for redesign because infrastructure was built in the wrong place. I've seen tunnel projects not meeting in the middle. The biggest blunders I've seen in my career were due to the confusion between grid versus ground, and in my opinion, it's talked about far too rarely and oftentimes misunderstood. Today, we're going to dive into exactly what grid and ground-based coordinates are, why we would choose one over the other, and how to convert between the two. This is a follow-up to my previous geoids video where we started to break down the vertical component of geodesy. Today, we will dip our toes into the horizontal aspect of geodesy. The topic of map projections really deserves a dedicated video on that subject alone, but just to lay some groundwork for this video, I'll try to cover the basics. A map projection is basically the transformation of coordinates from Earth's curved surface onto a flat map, UTM being an example. When we use GNSS, we are initially deriving XYZ Earth-centered, Earth-fixed Cartesian coordinates referenced to a specific ellipsoid. Those are then converted into latitude, longitude, and ellipsoid heights, and then those are converted once again into grid coordinates in the mapping projection of your choice. This conversion from latitude and longitude to grid coordinates allows us to make 2D maps and also significantly simplifies the math we use to navigate in our maps, such as calculating distances, areas, and angles. If you've never done spherical trigonometry, take my word for it. Something as simple as inversing between 2 points that have northings and eastings becomes quite the task when those points are in latitude and longitude. So what's the issue here? We now have our points in a manner that allows us to make easy, straightforward calculations and can visualize them on a flat mapping grid. It seems like we solved the problem. Well, we did solve a problem, but we also introduced others. When we project a round Earth onto a flat plane, we introduce distortion. Try to flatten an orange peel without ripping or warping it. To transform coordinates from the surface of a round Earth to a flat map, we basically take what's called a developable shape, or a shape that can be cut, unrolled, and flattened without warping, and overlay this shape around the round Earth. Imagine the Earth's surface is clear with lines of latitude and longitude drawn on it. If we wrap a cylinder around the Earth and place a light at the center of the Earth to project the shadows of the lines of latitude and longitude onto the cylinder wrapped around it, when we cut and unwrap the cylinder and lay it flat, the lines of latitude and longitude will look very different than they did on the Earth. In this example, the size of the objects and the spacing of the lines of latitude on the Earth near the poles grow significantly, and the lines of longitude always point directly up on the page, perpendicular to the lines of latitude, meaning that grid north does not converge to a single point, whereas the lines of longitude on a globe all converge to the rotational axis. True north at every point on the round Earth points to a single location, the rotational North Pole. If you've heard the term convergence or grid convergence before, it's describing the difference between grid north and true north. The map projection has distorted the size and shape of the Earth. Where that cylinder initially touched the round Earth or reference ellipsoid, there is actually no linear distortion at all. But the further you move away from that line of intersection on that mapping projection, the more the distortion is increased. Depending on where we want to minimize distortion, we may choose a developable shape other than a cylinder, such as a cone for example. Or we may choose to flip that cylinder on its side so that instead of the distortion increasing as you travel north-south, it increases as you move east-west. If you choose this orientation for your cylinder, then break up the mapping projection into a bunch of different zones. By placing many of these flipped cylinders over the ellipsoid, you can limit the amount of distortion each cylinder or zone has. Remember, the further away from the line of intersection you are, the more distortion there is. So if you add numerous zones, each with their own line of intersection, you will inevitably be closer to one of those lines. This is actually exactly what the UTM projection does. If you've heard the term zone 10 or zone 24, it's actually a new cylinder that's been flipped on its side with only 6 degrees of longitude being mapped per zone because again, in that narrow strip, distortion is relatively low. Another method that is used to reduce mapping projection distortion, which UTM also uses, is that instead of the developable shape only touching the ellipsoid along a single line, also known as a tangential projection, the developable shape cuts through the ellipsoid, which creates 2 lines of zero distortion. This is referred to as a secant projection. This again reduces the relative distance and therefore the distortion of a point to one of these intersection lines. In this situation, the radial distance between those zero distortion lines that intersects the ellipsoid, also known as the standard lines, is longer than the chord distance between those 2 lines. The chord distance representing the map projection in this situation. As you can see, we have to shrink the radial ellipsoidal distance down and everything on it to fit onto the grid distance. This is accomplished by applying a linear scale factor. Because the mapping projections we use for grid coordinates are usually conformal, which basically means the angular relationship between points is preserved over a small area, if we appropriately handle the linear distortion via a scale factor, we are able to effectively translate our geographic coordinates, which are GNSS likes, to ground-based coordinates, which we like. Before we dive into scale factors, let's first define a couple of terms: grid coordinates and grid distances, and ground coordinates and ground distances. In the context of this video, we can define grid coordinates as the northings and eastings of a point in a known mapping projection, and the distance between 2 points on a map projection would be the grid distance. Likewise, ground coordinates can be defined as the northings and eastings of a point not in a known map projection, but typically in a user-defined coordinate system that isn't directly georeferenced. Similarly, the distance between 2 points on a ground-based system would be a ground distance, or the horizontal distance between 2 points on the surface of the Earth. The primary distinction between the two is that a grid distance between 2 points on a map projection will not equal the ground distance between the same 2 points on the Earth's surface. When we typically think of distance, we are dealing with ground distances. Measure a horizontal distance with a tape measure or EDM, that's a ground distance. In a perfect world, everything would be in ground distances and ground coordinates. Using grid coordinates and grid distances means we have accepted some level of distortion for ease of use. For example, if we measure 2 intervisible points perfectly with GNSS and UTM, both with ellipsoidal heights of 0 at the center of a particular zone, and get a distance between the two of 700 meters, and then grabbed a really long tape measure and pulled tape between the two perfectly, that tape measure would read a ground distance of 700.280 meters. But that doesn't mean we can't obtain ground distances when we use GNSS. This brings us back to scale factors. There are 3 different scale factors we will look at to help us convert grid distances to ground distances and back again: elevation scale factor, grid scale factor, and combined scale factor. To turn that grid distance we measured with our GNSS of 700 meters into the ground distance our tape measure gave us of 700.280 meters, we scale the grid distance by the inverse of the local combined scale factor. You may have seen this abbreviated before as CSF. The combined scale factor is the product of the other two scale factors. The grid scale factor, also sometimes called simply the scale factor, and the elevation scale factor. Let's first look at the elevation scale factor. The elevation scale factor is calculated from a fairly straightforward formula. The average radius of the Earth, r, is divided by that same value plus the height above the ellipsoid, h. You can see when the point we're trying to calculate the elevation scale factor for is on the ellipsoid, a value of 1 is returned and no distortion is added from the elevation scale factor. But as the point gets further and further above the ellipsoid, the scale factor gets smaller and smaller, which in turn increases distortion. Keep in mind that doesn't mean just because the point has an ellipsoidal height of 0, there is no distortion being added. We still need to apply the grid scale factor, which we will explore momentarily. When a calculated elevation scale factor is multiplied by a ground distance between 2 points on the surface of the Earth, it reduces that ground distance to an ellipsoidal distance. An ellipsoidal distance is the distance between 2 points projected on the reference ellipsoid. But we want to be able to convert ground distances to grid distances and back again, not necessarily the distance between 2 points on the ellipsoid. One more thing to note is that while this scale factor is called the elevation scale factor, it's actually the scale factor dependent on ellipsoid heights, not elevations in the way we typically use that word. Some have argued that maybe it should be called an ellipsoidal height factor, and I would have to agree there. After we apply the elevation scale factor, we then need to apply the grid scale factor. This will allow us to reduce that calculated ellipsoid distance to a grid distance, or the distances between 2 points on a mapping projection of our choice. Now, the equation for grid scale factor is much more complex with a lot more variables. Luckily for us, we don't need to calculate either of these scale factors by hand. There are several methods to get this value. NGS has a tool called the Coordinate Conversion and Transformation Tool, or simply NCAT, that can calculate the combined scale factor as long as we know the ellipsoid height at that point. Opus or NRCan's PPP will also provide us with the combined scale factor at the point of the data we uploaded. And StarNet will give us scale factors for every single point in an adjusted network. We approach these scale factors as a two-step process just to give you a clear picture of what each one does, but in reality they can be combined into a single step conversion. Ground distance is equal to the grid distance multiplied by the inverse of the combined scale factor, and grid distance is equal to the ground distance multiplied by the combined scale factor. So now we know how to derive a combined scale factor of a point, but that scale factor is only correct at that exact point. As we move north or south, east or west, or change our ellipsoidal height, our combined scale factor changes. And since the combined scale factor will be different at either end of a line and everywhere in between, we won't be perfectly converting that grid distance into a perfect ground distance. Some minor distortion is added. For example, point A on one end of the line may have a CSF of 0.9996123, and point B on the other end of the line might have a CSF of 0.9996124. We will get two different ground distances depending on which CSF we choose. If we want to convert a grid distance between 2 points to a ground distance, the distortion caused by the conversion would be reduced if we either calculated the CSF at the midpoint of the line or calculated the CSF at either end and averaged the two. What we ultimately want to do is to convert a set of grid coordinates to ground coordinates. For example, we want to convert a project site that we surveyed using GNSS that's in a mapping projection into a ground-based coordinate system. Why? Because we generally want to know the true ground distance between 2 points. If I'm laying out a building, the client will have plans of that building that are based off true ground distances, not grid distances. The builders aren't using grid tape measures. A grid distance of 100 feet in Denver is different than a grid distance of 100 feet in Florida. If grid distance is a product of a true ground distance scaled by a combined scale factor that's always changing depending on where you are, how can a 100-foot grid distance be a constant value? One issue we must be aware of is that when we convert grid coordinates to ground coordinates, it won't be a perfect conversion because the combined scale factor that we choose to scale a set of points by will only be correct at one location within the project. Yet that scale factor is being utilized for all coordinates. The amount of error we would be adding by using one scale factor over an entire site depends on how big the site is and the mapping projection being used and where you're at in that mapping projection. Let's look at a few examples to help illustrate some differences between grid and ground and the effect of choosing one scale factor for an entire project. This table shows a set of coordinates in Florida and the calculated combined scale factor in both the local state plane map projection and the local UTM projection. As you can see, the state plane combined scale factor is significantly closer to 1 compared to UTM, which now we know means less distortion. When the state plane map projections were initially established, they were done so in a way that the maximum distortion caused by the grid scale factor should have been less than 1 to 10,000, with the thought being that the survey instrumentation available at the time should not produce accuracy significantly better than that, and therefore grid to ground could essentially be ignored in most situations. This was accomplished by limiting the size of map projections. Since then, instrumentation has improved quite a bit, and we can now quite easily survey better than an error ratio of 1 to 10,000. In this location in Florida, a state plane grid distance over 1,000 feet or 305 meters in state plane is converted into a ground distance of about 1,000.05 feet. This gives a change in length of 0.05 of a foot or about 1.5 centimeters. So at this location in the map projection, can one ignore the grid to ground conversion and keep things simple and only work in grid? It depends. For most projects, that distortion amount is probably acceptable, but if one were performing high accuracy layout for an engineering project, you could get yourself into some trouble by allowing 0.05 of systematic error over 1,000 feet. But if we look at the same project in UTM this time, which carries much larger scale factors because the zones are much wider, and hence the distance from the standard lines or lines of zero distortion are increased, we're looking at about 0.4 of a foot of distortion or about 12 centimeters over 300 meters. This is quite obviously not acceptable in almost all surveying projects where ground distances are expected. If the project was designed in grid, which is the case sometimes, obviously we would not convert to ground coordinates. Let's look at another example. If we surveyed a 1,000-foot property line with GNSS and left it in UTM, and that property line was originally established in ground and reported that new length is 999.6 feet, you can imagine that property owner might be upset that you just shrunk his property by almost half a foot. Now imagine if we staked out building corners incorrectly by almost half a foot. And this is just at 1,000 feet or 300 meters. When we extend this distance out to 5,000 feet or 1,500 meters, the distortion in state plane grows to about 0.3 of a foot or almost 10 centimeters, and the distortion in UTM grows to almost 2 feet or 60 centimeters. One last point on this example. These state plane scale factors were calculated in an area with small ellipsoid heights, which means distortion caused by the elevation scale factor was relatively small. What about when we're somewhere such as Denver, where we have ellipsoidal heights of over 5,000 feet? If we look at monument AE 5249 in downtown Denver, we can see it has a state plane combined scale factor of 0.99974875. Much further away from 1 compared to what we saw in Florida. And if we look at that same 1,000-foot example again, we can see that instead of 0.05 of a foot we saw in Florida between grid and ground, we now see 0.25 of a foot over 1,000 feet of distortion between grid and ground in Denver. Elevation really matters here. So just because you can get away with not converting grid to ground in some places doesn't mean you can always do it. Check your local combined scale factor before making that decision. We really only want to use the combined scale factor from a single point when we convert a project from grid to ground, and the choice of which point to use to calculate the combined scale factor will affect the distances between every point in the network. As you can see, every point in this example project has a slightly different combined scale factor. So depending on which point we use, and hence which combined scale factor we use, we get slightly different ground distances. If we use the CSF from point 1, we get a total project ground length of 12,728.569 feet. And if we use the CSF from point 10, we get a total project ground length of 12,728.634, a difference of 65 thousandths or about 2 centimeters. But keep in mind that's almost over 13,000 feet or almost 4,000 meters. And this is easily cut in half to about 1 centimeter by choosing a central point in which to calculate the CSF from. And this does not mean that if we were to set up on the edge of the network and backsite a point 300 feet away, we would see 1 centimeter of error in the backsite distance. This error is relative, so at that 300 feet, if we measured a perfect ground distance with our total station between the shifted ground points, we would be out by a fraction of a millimeter. This could change though. If you're working on the side of a mountain or in areas of large vertical relief on projects that require the highest level of accuracy over large spans, it's not unheard of to break up a project and use multiple scale factors. This would, however, be the exception, not the rule. If you have a project with 2 or more scale factors being applied, you're essentially creating 2 or more separate and distinct coordinate systems. You would not want to set up on the edge of one and backside a point in the next coordinate system over. They are not going to be scaled about the same 2 points and won't agree with each other properly. 99.99% of the time, using multiple scale factors is not needed and is more trouble than it's worth. But this starts to explain one reason why we can't have a single statewide ground coordinate system. One thing to keep in mind, some projects are designed using grid coordinates and should not be converted to ground. A roadway corridor project would be an example. 100 miles of road would mean numerous scale factors over a span of that distance, and there really isn't an accuracy need in that style of project where the difference between grid and ground is going to affect much. An error ratio of 1 to 10,000 is negligible when we're talking about earthworks and asphalt. Now, if that roadway came to a fairly substantial steel bridge crossing, that's where things could change. That section may be required to be designed and staked in a local ground system. So how do we go about converting grid coordinates of a project to a ground-based coordinate system? We typically pick a point in the middle of the project that has an approximately average elevation and obtain the combined scale factor for this point. We can call this our scaling point. We then scale all the northings and eastings of the surrounding points using the inverse of the combined scale factor. Typically around that scaling point, but it's not necessary. Scaling about 0 northing and 0 easting is a common practice as well. The absolute position will be different depending on which point you choose to scale about, but the relative distance between the points in that coordinate system, which is what we care about, will be the same as long as the same scale factor is used. Whichever method you choose, just be sure to note your scale point location and the scale used, as others using your data may want to convert the data back to grid coordinates at some point. There are many ways to do this. It can be done in Excel, in AutoCAD by either just using the scale factor command or using the transformation tool. For more information about that method, check out my videos, Scale Factors and Kogo and Civil 3D video. And StarNet has an extremely handy method for exporting adjusted coordinates in both a grid and ground-based coordinate system. There has long been a debate when converting between grid and ground-based coordinates. Should one truncate their ground coordinate values to avoid confusion between the two coordinate systems? What I mean is that right now, if we scaled about our scaling point, we have created another coordinate file, a scaled ground coordinate file, that is slightly different than the original grid coordinate file. It wouldn't be difficult for someone to mistake one of these coordinate files from the other. The advantage of not truncating values is that the ground-based coordinates will fall approximately in the right absolute location, so they will still line up decently with other data sources such as aerial imagery. The con is that it's easy to mix the two coordinate systems up. A method that is often used to avoid this confusion is that the first few digits in the ground system on both the northing and easting are removed, so that, for example, 1.52 million meters northing turns into 20,000 meters northing, and 510,000 meters easting turns into 10,000 meters easting. This way, as soon as someone sees these coordinates, it's abundantly obvious that these cannot be in a grid mapping projection, as grid coordinates often use false eastings and false northings that provide values that are much larger. My strong recommendation is that when you do transform a set of grid coordinates into a ground coordinate system, you should always be very clear about the metadata of your transformation. It is very possible that someone in the future would want to convert your data back into grid. If you applied a scale factor about a particular point, truncated values without being very specific about what you did, then there really is no way someone could go back and convert your ground coordinates into grid coordinates without taking some approach that involved going out into the field, taking a bunch of GNSS measurements on your control points, and creating a transformation that will undoubtedly add a lot of time and error into the process when it can be done very easily in the office. The method that I've adopted is that I'll create a text box somewhere on my control report that gives a small step-by-step process on exactly what to do to convert the supplied ground coordinates back into grid coordinates. For example, step 1, scale all points about 0.120 by 0.999961234. Step 2, add 1.5 million to the northings and 500,000 to the eastings. Are these grid coordinates? Hopefully after watching this video, you can confidently understand this question when it gets asked of you. Few things scare me as much as when I ask this and the surveyor that collected the data gives me the deer in the headlights look. In my opinion, this topic should be thoroughly understood by every single person collecting, delivering, or processing geospatial data. There really is no room for mistakes here. The consequences are just too dire. Even though this may have looked fairly complicated if this is new to you, we're lucky that there are tools that can help us out here. Like I said before, StarNet really makes the handling of scale factors an absolute breeze as long as you understand what they are doing and when to use them. Civil 3D does a fairly good job too once you get a handle on the transformation tool, and if you live in the United States, there has been some momentum on moving to low distortion mapping projections, which will significantly reduce the ground to grid deviation. But that's a topic for another video. Thank you all for taking the time to watch this, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time. Map projections. It's to ground coordinates. Dude, what the Let's look at another example. Let's look at another example. But this starts to explain that. Holy smokers.